So let's talk about electric field when you've got more than one charge. If you've got an electron here, he's got a buddy, a proton, over here, what happens to our electric field? It's pretty obvious that the force, the attractive force between these two, is going to act along this axis between them. So we can imagine there's an electric field line that looks like this. But what if you've got a test charge out here, or over here, or even back here? This is a little bit more tricky. Let's think about the individual electric fields of these two particles. For our negative charge, you will see electric field lines pointing inward like this, which hopefully you caught me. I've drawn this electric field line backwards. It should be pointing this way because our positive charge would be attracted to the negative charge. And for our positive charge, you'll see electric field lines pointing outward like this. So hopefully you remember that superposition says that electric field lines can cancel out, but it also means that they can be added together. So let's think about adding up these electric field lines. If you've got an electric field line from our positive charge that looks like this, and one from the negative charge looking like this, you can add them together to get a shape more like this. And the same goes for down here. And this continues for all points on our electric field here. You can see adding these lines together and these lines together. And for these lines farther away, you can just kind of have to imagine where they might go. The lines from the positive charge will be pointing toward the negative charge, and these lines here will be going toward the negative charge coming from the positive charge. This configuration with one negative charge and one positive charge is called a dipole because it's got a negative pole and a positive pole. There's one other particularly important configuration called a capacitor. This is something you'll find in a circuit, and it stores energy. We'll talk more about energy in electric interactions in later lectures. Basically, a capacitor consists of a positively charged plate, a slab with distributed charge, and a negatively charged plate. These are both conductors, so as you can imagine, we'll have negative charge along the surface and positive charge along the surface here. The amount of negative charge is equal to the amount of positive charge. Let's think about the electric fields. For our negative plate, you'll have electric field lines pointing inward, nice uniform electric field. And how about over here? We've got positive electric field lines pointing this way and out this way. So let's think about superposition. We'll have this line and this line adding up. So the electric field strength is actually stronger for these two plates than it would be for just one plate by itself. And it points in this direction. So what about these? Since the electric field is uniform, it doesn't decrease in space. So that means that this line here also affects this line way over here. It's also true that the electric fields here affect these. We end up seeing some canceling out, so the electric field outside is 0. This is very similar to the Faraday cage situation because you've got conducting plates surrounding some kind of space, and then there's an external space. In this case, the external space is experiencing no electric field. In the next lecture, we'll do some practice with writing electric field diagrams. See you soon!